Welcome everyone to a new video. In this video I will explain the basic principles of an MRI. Well, we first start off with what is an MRI. MRI stands for magnetic resonance imaging. Well, as you can see here on the right we have this big device that includes a magnet, and this magnet will be turned on, and eventually by means of the magnet and the radio frequency pulse, which is generated by the radio frequency coils, a RF pulse will be generated, which leads to the protons starting to resonate, which is what's called magnetic resonance, and this eventually will lead to an electric signal that's returned back to the machine, and this can be put into an image, as you can see here on the left hand side on the computer, and this image can be used to differentiate such as different tissues, which can lead to noticing abnormalities, or for example also potential tumor growth. Okay, so how does this device work? Well, with protons, protons are almost in every type of tissue, because protons are subatomic particles that have a positive charge. So for example, they can be found within our muscle tissue and within our fat tissue, and also in water, which is why we are also made up of 70% of water, so a lot of water is in our body, therefore it's also easy to detect these particles. Okay, so so water is H2O, it has two H atoms, so an H atom is also a proton with one proton. This H, there's something special about this proton, this H hydrogen atom, because this hydrogen atom acts as a kind of small magnet, because it has a delta positive and a delta negative side, which makes it act like a kind of magnet, as you can see here with a north and south pole that acts as a magnet. Well, so how does the machine work? Well, the machine has a big magnet. When turned on, this magnet creates a magnetic field. This magnetic field is referred to as the B0, and B0 is in the Z-axis, so it's in the longitudinal axis of the patient. And well, what happens is these patients, of course, has a lot of different types of muscle, fat, etc., all types of different tissues, and these tissues include protons. Well, when this magnetic field is turned on, these protons will either go into the parallel direction, which is parallel to B0, or anti-parallel. But there's a slight majority of protons that align in the parallel to B0, and this results in the net magnetization factor being aligned with B0. So that it isn't that easy, because the individual protons also have a nuclear spin, or this is also called precession. While these protons, as you can see here on the left here, these protons also spin around its own axis. So every proton has a kind of spin around it in a transverse axis. And well, how does this spin actually work? Well, the spin is predictable. So the spin will go according to the Larmor equation. And the Larmor equation is that the frequency of the precession, so the precession frequency, is equal to the gamma times B0. And the gamma is a gyromagnetic ratio, which is a kind of constant that's different for the protons in different types of tissues. And then also the strength of the magnetic field is what we induce with the magnet of the MRI, and that is in clinical occasions is oftentimes 1.5 Tesla or 3 Tesla, depending on what we want to measure or see. Okay, so explaining how this essentially works. As well, we have the Z-axis here, which is the longitudinal axis, and the XY axis, which is the transverse axis. The net magnetization factor initially, when the B0 is just turned on, is aligned with the Z-axis, so this is equal to the B0. What will happen is we will induce a 90-degree RF pulse, a radio frequency pulse, which will make the net magnetization factor turn from the Z-axis to the XY axis, so to the transverse axis. So then we have the net magnetization factor in the transverse axis, but this is a high energy state, because we've just put energy into the system, so these protons are energized, so they're in high energy state. But of course this energy will decay, and it will want to go back to the low energy state, which is aligned with the Z-axis and to B0. Well, what will happen is that the Z-axis, so the transverse energy, will then decay, and the Z-axis energy, so the longitudinal energy, will then recover. And what happens is that the protons recover and decay in different different time speeds, which allows for different tissues to act differently, so that we can differentiate between different tissues. As you can see here, the recovery of the z-axis is called the T1 relaxation time, and we call the T1 relaxation time when 63% of the initial net magnetization factor is recovered. And then also we have a T2 relaxation time, which is when 63% of the transverse net magnetization factor is decayed. So here you can see that we have a table that, for example, cerebrospinal fluid has a T1 of 4000 and a T2 of 2000, and when comparing that with gray matter, for example, it has a lower T1 and also a lower T2. So therefore we can differentiate, for example, between water or cerebrospinal fluid and gray matter, which makes it easier to show up in the image that we want to see. Okay, so this isn't that easy, that we just only have the 90 degree radio frequency pulse, the RF pulse, because there's also a concept called inhomogeneity, which shows that there isn't uniformity everywhere. So for example, you can see here this proton, it experiences a different kind of pull from the magnetic field than, for example, this proton will or this proton will. Well, so how do we account for that? It's when we have here the pulse scheme. We initially have the 90 degree pulse. That also creates a kind of energy, because like I want to show you, we have the z-axis and the xy axis, and when the decay of the decay happens, we get a kind of spiraling form, because of course the precession is also going, the protons are also precessing, which allows it for a kind of spiral to form, and the spiral will put energy back into the system, which we can turn into an electrical signal, and therefore we can create a picture. And this is called free induction decay. So that is the creation of the energy from the protons back into the system. Well, so therefore we do not have uniformity yet, but how do we create that? The RF pulse also creates a kind of MRI signal, but the signal is very opaque and we can't really read it because the uniformity is not achieved yet. Well, how do we do that? Well, we also stimulate it with a 180 degree RF pulse, and this is kind of difficult to understand initially, because the 180 degree RF pulse allows for uniformity to occur, and therefore we get a clear signal, and the signal is also referred to as an echo, and this echo is then used to create good quality image. And so from the RF pulse to the echo, we call that the time to echo, the TE. And then from 90 degree pulse to 90 degree pulse, we call that time to repetition, so the TR. Okay, so kind of analogy that's oftentimes used with MRI to understand the 90 degree and 180 degree pulse to create uniformity. Well, we have two lines with two cars, a purple car and a yellow car. Well, they want to start. They start a street race, for example, at the start line. We give them X amount of time, and in X amount of time, the purple car has gone further than the yellow car has. But if we at this exact moment let them turn around and go back to the start line, theoretically, these cars would reach the start line at exactly the same moment. And this is kind of what happens with the protons, and therefore we have a uniformity within the protons, and that allows us to get a clear signal that we can turn into an MRI image. If you've enjoyed this video, don't forget to like and subscribe, and thank you for watching.